this week. It's really a pleasure to have Dan Orazio visiting and being the speaker of today. I've known Dan for a long time. He was actually here many years ago, so before starting his PhD. He was a Fulbright fellow for 1 year, 2009 to 2010. And he took classes here, one with me, one with Prasenjit, and another. So he was a student here long ago. Then he started his PhD at Columbia University, working with Zoltan Ayman. And then he already started working on one of its main topics, which is the astrophysics of gravitational wave sources, in particular, supermassive black hole binaries, how to model them, how to understand their dynamics, but also how to find them, because his work is also going into making observational predictions and really trying to guide the observations. And he has worked on also other topics in high energy astrophysics, again, from the theory to the phenomenology of many interesting systems, especially complex binaries. Then after his PhD, which he got in 2016 at Columbia, he moved on and was a Einstein Fellow at CFA at Harvard, and then subsequently an ITC Fellow, the Institute of Theory and Computation Fellow, still at Harvard. And then from 2020, he became assistant professor at Niels Bohr Institute, where he's still now. So it's really a pleasure to host you here, and the talk will be about finding supermassive black hole binaries.
Great. Thanks so much, Lucio, for the introduction. And yeah, as Lucio said, I started my astrophysics career here, taking courses with Lucio, and Prasenjit and I wrote a paper on dynamics and GR back then. And since then, I've been thinking about gravitational wave astrophysics, and really with a lot of focus on these supermassive black hole binaries, which is going to be the subject of today's talk. So you'll notice I amended the title a little bit. It used to say how to find supermassive black hole binaries and what to do with them. But the second part I'm going to leave to your imaginations, and we can talk about it afterwards. I'm going to focus on how to find these systems and how they interact with their environments. All right. So when you think black hole binaries, I think one of the first things that comes to mind, at least for me, is gravitational waves, right? Because these are some of the best sources of gravitational waves, which we're now detecting. So I figured I'd start just with this kind of spectrum, this gravitational wave spectrum, the gravitational wave sky, from low frequency gravitational waves to high frequency gravitational waves. And, as we've been hearing about over the past, almost 7 years now, is that at the high frequency end of this spectrum, the LIGO, Virgo, CAGRA collaboration has detected of order almost 100 emerging compact object binaries, mostly black hole binaries, with masses in the range of a few up to 100 solar masses, right? And one of the big questions in astrophysics, at least, is how are these compact object binaries formed? What are the astrophysical environments that form them? What can we learn about astrophysics from studying the demographics that we have now have of this population? Okay, I mean, this is exciting, and it will continue to be for a while, but just like in the electromagnetic spectrum, when we went from optical to radio, for example, we discovered a lot of new things. And I think one of the exciting, hi Dennis, pieces of the future of this field is going to the low frequency gravitational wave sky. So lower frequencies meaning millihertz down to nanohertz, parts of the spectrum we haven't probed yet, but we're going to in the very near future. So LIGO isn't detecting gravitational waves in these frequencies, but there's two main instruments or classes of instruments that will detect gravitational waves in this regime. One of them is LISA, the Laser Interferometer Space Antenna, and that'll detect mergers of, million, 100,000 to tens of million solar mass supermassive black hole binaries when they merge, and out to, very far distances, redshifts of 20 or so. And, a number of people here are involved in that. But another one, if we go to even lower frequencies, now near nanohertz frequencies, there's a different type of experiment that can detect these lower frequencies gravitational waves, ranges of experiments called the pulsar timing arrays. Now, instead of having an interferometer that detects this small passing gravitational wave distortions, you instead make a galactic size detector where you really precisely time astrophysical clocks, which are the millisecond pulsars. And by timing these for a long time, right now, these pulsar timing arrays have been timing for 15 years or so. You can detect the in spiral of the most massive supermassive black hole binaries. So billions to tens billion solar mass systems that are not merging, but making their way towards merger. And if you put together all of those different in spiraling sources throughout the universe, they add together in some type of stochastic noise, which creates this astrophysical background source, which we're very near to detecting. I'm, quite excited to say, actually, because only in 2020, there was some evidence of this possible background. And if you look at that background and ask how much longer should we look at this until we're sure it's gravitational waves or not, some of the estimates now are that you need a 15 to a 17-year data set to do this, whereas the data set a few years ago was 12.5-year data set. So the predictions are that perhaps even in this coming few years, there could be detections of this background. So the low frequency sky is actually a lot nearer than I think it could be next year. So we'll see what happens. So that's why I think these supermassive black hole binary sources are exciting. We're going to see them in gravitational waves soon. But the rest of this talk is not about gravitational waves at all. It's about the astrophysical setting of how we create these mergers. Yes. So the merger of two supermassives, we're going to see in low frequency gravitational waves. But how do they arise? So here's the cartoon picture, right? These supermassives are at the center of galaxies, and galaxies merge. All right, so that's step one. We know that after this merger, there are a number of processes, mainly dynamical friction, which can bring those two supermassives to the center of a new galaxy where they form a binary. All right, and if that binary gets tight enough, close enough, then gravitational wave radiation becomes efficient enough to carry away energy, angular momentum, and merge that system and create a big burst of gravitational waves that we're going to detect, I hope. Okay, but there's a step two. In between, there's an open question often referred to as the final parsec problem. How does that binary interact with its environment in the galactic nucleus to get close enough for this stage to be efficient? Right, so do supermassive black hole binaries merge? The galaxies do, but do the supermassives, and what mediates these mergers? This is a lot of what I think about here in this step two. And one of the ways to answer this is understand how this will understand the environment that the binary interacts with and how that interaction, how it goes. And so the subject of this talk today is thinking about how that binary interacts with gas, because in these galactic nuclei, you expect there to be lots of gas that could, for example, be torqued down to the center of that galaxy after the galactic merger. And so what does this gas interaction do for the binary? And there's two main things, two kind of channels that I think about here. One is that gas, just like a satellite moving through the Earth's atmosphere affects the orbit, gas affects the orbit of this binary and could push it past this possible final parsec bottleneck towards the gravitational wave stage, or it couldn't. Either way, we need to understand this interaction for predicting populations of supermassives in this regime. But gas falling onto a binary does another thing. Well, falling onto black holes does another thing. It lights them up, right? We see quasars and AGN, quasars at the edge of the universe because accretion onto black holes is incredibly efficient and can be incredibly bright. This should also happen onto binaries. So by modeling this gaseous interaction, you can also try and predict what are the electromagnetic signatures of these accreting supermassive black hole binaries at a stage earlier in their lives, before they're emitting a lot of gravitational radiation. And by doing that, figuring out how to find these, we hope to take a census of these. When you can do that, you have demographics to try and study a population and figure out what is happening in this step two. So to really solve this final parsec problem, I think this is, the basic approach. We need to find these systems in nature to see how they actually come together and merge. So I want to start with some ideas we've been working on over the years to look for these, to find these systems, to find some kind of smoking gun evidence. Because to date, there is really no definitive evidence for these supermassive binaries in this sub-parsec separation regime. But there are candidates, and I want to tell you about candidates and methods for looking for these. Okay, so let me just lay out quickly. This is something that's been going on for 40 years, maybe at least, looking for these systems. So I want to just write this number line here of different ways to look for these or find evidence for them as a function of the separation of the two black holes. So we talked about gravitational waves. When they merge and near merge, we hope to find a boundary condition for their life and evolution in gravitational waves. And on the kiloparsec scales, the large separation scales, there is indeed images of two accreting black holes nearing each other. I think the record holder in closeness is of order a few parsecs. Okay, but in between, there's a number of different ways, ideas people have been thinking about. For example, these two things have jets. Are those jets wobbling around due to orbital motion? After they merge, do the jets flip and create some interesting shapes on the sky? There's monitoring of broadline emission that could be moving back and forth due to orbital motion. Something I could tell you about later, but not today. We're thinking about how something like the EHT, the Event Horizon Telescope, millimeter very long baseline interferometry, could directly track the orbits of these if they're emitting in the right frequencies. And this one here that I put at the top right, periodic light curves, is what I'm going to focus on now. So I'm going to explain what this method, which I think is a promising method, especially in this coming era of time domain astronomy, where we have these large all sky surveys mapping out time domain variability of quasars. It's going to be very useful. So what is this periodic light curve method? Well, to describe it, I like this cartoon schematic of an active galactic nucleus. At the center is this black hole. It has this pink accretion disk around it, which is creating all the direct optical UV emission we're seeing from this AGN. And then surrounding it is its kind of astrophysical environment. There's a dust torus, there's this broad line region, there's a jet maybe. And the whole name of the game here is just to replace that with 2 and ask, how does this picture change? Because if there are, as I said in the beginning, if AGN are driven by accretion on the single black holes, and we expect there to be black hole binaries sometime, then this should happen. What does it look like? Can we tell the difference between the two situations? And then the idea with periodic light curves is that if you do have this binary, and in the subparsec regime, that binary could have orbital periods of order years, sometimes less, sometimes more, depending on the mass and the separation, then that churning, that orbital motion, that very steady Keplerian period could imprint itself on the light coming from the quasar. And so how does it do that? That's the question. And how does that do that uniquely, showing that it's a binary and not something else? Before I tell you how this periodic variability might occur, I can tell you that there are such candidate systems. So over the last, really on the gravitational wave timescale, over the last 5 to 7 years, a number of groups have looked at time domain surveys, for example, the Catalina Real-Time Transient Survey, over 10 years, 10 plus years, monitoring hundreds of thousands of quasars, and asked of the light curves of these quasars, do any of them have any type of periodicity to them? And so now there are about 150 candidates for these periodic light curve quasars. Question is, are they really periodic? Because AGN also exhibit lots of noise, damped random walk noise, and other types of noise intrinsic to these systems. And at the moment, of these 150, I would say probably a number of them, maybe even half, are no longer periodic, but this is work that's going on. But once you've monitored them long enough and determined that they are periodic, the question then is, well, is that, again, due to a binary or something else? So these are out there. We want to explain them and understand which of them might be real systems. So then how is this periodicity created? Well, one perhaps obvious way, maybe not, is just due to accretion variability. So this is a hydrodynamical simulation of gas falling onto a binary. And from this simulation, you can ask, the first question is, does gas actually get onto the binary? You might not expect that it would, because the binary is acting as a propeller here, torquing the gas outwards. Maybe it can't fall onto the black holes. But what we've found over the last, I guess the last 10 years of work on this is that gas can accrete at the same rate as it would for a single black hole, and that it's uniquely modulated at the orbital period, but also depending on the parameters of your binary, many different harmonics of the orbital period that you can predict. And so this is ongoing work that we're expanding upon now. And it is an interesting possibility in a way that you could create that periodic variability probably should be created. But I'm not going to focus on it because something I really like, a little more, I would say, simple and perhaps robust, is that even if you don't have variability from hydrodynamics from accretion, as long as you have accretion onto the system and it's bright, then relativity happens. So essentially, there's a number of different scenarios where you would just get steady emission from this binary accretion. But because there is an orbital velocity, then you expect the special relativistic effect, Doppler boosting, to create some variability. And also, depending on your alignment of the binary inclination to the line of sight, there can also be some gravitational lensing. So let me explain what this does for us with some pictures here. Okay, so let's imagine we're looking at, on the top here, we're looking at this binary system. And say the smaller black hole is accreting and giving off light, and it's inclined at some angle to our line of sight. Okay, now at the bottom, imagine again that this guy is emitting light. Okay, and so the Doppler boost picture just says that if this is emitting steadily in its rest frame, when it moves away from us, it looks dimmer. When it moves towards us, it looks brighter, right? That's pretty simple. And what you get is a periodic variability. For a circular orbit, it's a sinusoid. For eccentric systems, you can imagine that shape changes predictably. Okay, I mean, that's nice. That creates periodic variability. But I think the powerful thing about this picture is that it makes a prediction, a multi-wavelength prediction, which I want to try and explain here with this picture. So the same scenario, that small supermassive black hole is emitting light at the top. And it's emitting, the important thing here is that it's emitting some spectrum here, log f nu versus log nu, and we're observing in some band. We're getting photometry, say, in optical, the V band. And so that spectrum has some slope to it. Okay, so as the orbit moves towards us, aberration and time dilation make it look brighter, but also blue shifting makes it look brighter. And how much brighter depends on the spectral slope of the emitting system. And that spectral slope is measurable. It's something you can measure if you have a spectrum of the emitting system. Okay, same things happens at redshifts, and the amount by which it gets dimmer, the amplitude of your modulation, is dependent on this measurable spectral slope. So what does that allow you to do? If you can get photometry in two different bands and spectra in two different bands, then you can predict, say we see this system in optical, and we get this periodic variation in optical, and we measure a spectral slope in optical. Then we do the same thing in ultraviolet. There should be the same period, same shape of variability, but the amplitude will be different by a factor depending on the two spectral slopes. So there's no free parameters. You can just predict that if you have periodicity in one band, it should be periodicity at a different amplitude in another band. And this allows you to try and say this, okay, this is periodicity, but it's also periodicity specifically due to Doppler boosting. Okay. And so a while ago now, there was a candidate system that came up that matched this quite well. Actually, this Doppler boosting was, we came up with it to describe this system. So this is optical V-band data on a quasar called PG1302. So this data is from the Catalina Real-Time Transient Survey. And I'm just going to show you quickly that there is a, of order of 5-year observed orbital period to this system, putting it in, a centiparsec separation. So almost in the gravitational wave driven regime if it's a binary with this mass and period. And so what we did is, this is one of few systems that does have photometry in optical UV and also spectra in optical and UV. And if you look at the optical and measure the spectral slopes in these two different bands, you predict the UV should look the same, but with twice the amplitude variability. And so this is a little bit of a messy plot, sorry, but this is the same system. The gray points are the optical, the blue and red are the predicted UV oscillations, and the blue and red points are the few UV data points that exist from Hubble and GALAX. And so in this first glance, it does match this prediction. And so this is, I think, an extremely interesting and strong candidate for a binary, supermassive black hole binary system. But what we have to do is wait and get more data and make sure that, this bears out over time. Because if this is a fluke of some manifestation of noise, the one way to check that is just to gather more data. So that's the Doppler boost. But I also mentioned lensing. So we looked at the left movie a minute ago. The right movie is the same thing. I've just inclined our binary closer to the line of sight. And what you'll notice is that as now this little light bulb, the secondary accreting black hole, passes behind the larger black hole, it's microlensed. That accretion is microlensed if it's close enough to the line of sight. And what that does is create these rather unique symmetric flares at these very specific places in the phase of your oscillation, right at the conjunctions of the 2 points. And so the second small one is if you assume that the primary black hole also is emitting light. Okay, so that's, a very unique light curve, but is this something that you would ever expect to occur? And so I can give you a quick idea. If we go back to these candidate, periodic systems and just use their orbital periods and their masses as an example, you can compute what is the probability that any given system is oriented correctly so that it will create a appreciable lensing flare. And the criteria here is just that this secondary passes within an Einstein radius of the primary lens. So you can ask, what is that probability just given, geometry? And assuming that you see a whole orbit, so you can treat this as a ring. In that case, you find for these systems, this probability, can be tens of percent, a few to tens of percent. So we're not beat there. There are 100 or so of these candidates, so 10% should do this. Then you can already start asking some questions. And then you can also ask, how long are these lensing flares? Do we hope to ever detect them given the cadence of our time domain surveys? And you can do similar calculation and find that these are weeks to months lensing events. So this is something that I think is pretty promising. And let me also show you a candidate system for this type of self-lensing. So this is kind of a wild looking light curve. This is from Kepler. Kepler was looking for exoplanets, of course, so it has very good photometry and very high cadence. And so I was giving a talk on this lensing idea a while ago, and somebody in the audience showed me this system, which seemingly has this wild flare, perhaps in the middle of a rising light curve like I showed you. And it doesn't quite match those circular orbit light curves that we just looked at. But if you allow the binary to be eccentric, you can get a whole range of different shapes. For example, one here that might look like perhaps this light curve. So, just to see, we modeled this system with our, Doppler plus lensing, pretty simple, might even call them, toy models, to try and see if we can approximate or fit this light curve and predict when this flare would occur again, if indeed this is a self-lensing binary system. And so if you zoom in on this flare, there's some interesting structure, but it's pretty symmetric. And so we fit this model, this 10 parameter model. It fits the flare nicely. And what's nice is that width and height of the flare really encode the orbital parameters. So without having this is not periodic, right? It's just one flare, but from that one flare, you can predict the period, which allows you to make a prediction for when this would flare again. And so at the time we did this, we had missed 2 or 3 flares, but we got a good deal of ground-based observation time from the Las Cumbres Observatory and from some X-ray data from Chandra. And we have been tiling that region, which is this third peak over there, since, we've been getting some data since then. And well, we're still analyzing the data, so I'm sorry I can't give you the complete answer, but essentially, I can tell you more about this really interesting system later. There is no, definitive huge flare, but we also haven't ruled out, given our cadence, that we missed it. So we're trying to understand how much the data constrains this system. Either way, this is an extremely interesting AGN. When you start, looking at AGN variability at this time scale and this photometry, we're apparently finding interesting things. So we're continuing follow-up on the system, and hopefully we have some constraints on the binary hypothesis very soon. But this is just one example. I think what's really exciting for the near future is how many of these systems like this would we expect to find if this is something that's happening in nature, this lensing of supermassive black hole binaries. And so there are a number of all-sky time domain surveys coming up and operating now. The Zwicky Transient Facility is operating right now. Gaia will have multi-epoch photometry in the near future. And I think the real gem of this, as many of you know, is the Rubin Observatory's legacy survey of space and time. So with some collaborators, Luke Kelly is now at Berkeley, I believe, and Roseanne DeStefano at Harvard, we went about trying to ask, given the best kind of predictions for populations of supermassives throughout the universe, how many could LSST, how many of these lensing systems or Doppler systems would we expect to find with LSST? Is it a lot? So what we did was put together some results of the Illustris. This is Luke Kelly, results from the Illustris simulation to give us some initial condition on pairings of supermassive black holes through galaxy mergers, and then using relatively simple prescriptions for binary hardening due to gas and stars and gravitational waves, you get a mock population of binaries at different separations and masses and inclinations, and you ask how many of those exhibit, given a certain survey like LSST, how many of those are detectable? Is there periodicity or repeated flaring detectable? So I'll just give you a quick result of this study, which you can look at too from last year. And it turns out that of all the different types of surveys we looked at, the only one with an appreciable prediction for an appreciable number of these systems is LSST after about 5 years of observations. So, I mean, I thought this is pretty exciting and optimistic for looking for these systems, is that if you look at this left plot here and you just plot the number of expected detectable lensing or Doppler modulations, given the sensitivity of LSST, then for orbital periods of order 5 years, this number can be tens, depending on a few different assumptions you make. And actually, the lensing is much more detective. Lensing is blue, Doppler only is orange, and that's because this flare can be a lot larger and kind of rise above confusion with AGN noise. For example, we added this kind of damped random walk noise as a confusion noise to this and said, when is this modulation of Doppler or lensing larger than that? And the lensing seems to be to do a good job. So I think this is promise. Yeah.
Question. As you showed at the beginning, that two is still very uncertain.
Yeah.
And so in this population model, there's always the problem how to bracket the possible time scale.
Yeah, I agree.
Did you have a kind of error bar in this plot? I don't see that.
Yeah, so that's something I discussed with Luke because he's been putting together these population models. And I think in this specific realization is really a choice for decay. So when you take that into account, I could say, well, maybe all of them stall at a certain separation, and then the error bar is large, right? But that brings me, depending on how much time is left, we could talk about step 2. So how much time do I have left, Pedro? Okay. Yes, so with that, of course, that caveat, this is a coupled problem. We don't know populations because we don't have observations, and we can't predict observations because we don't have populations. So this is part 1. We have to start looking for them. This is promising because at least in some realization of what we think is a reasonable model, there could be tens to hundreds of these systems, which would allow us to build up some demographics and study the population. Of course, we need to advance these models, put together accretion variability and Doppler and lensing in a more realistic situation, I believe. They're robust because they're based on relativity, but there's also a lot of other astrophysics to add in. And also, looking for these isn't trivial. You can just take your data and take a Fourier transform of it and look for periodicities, but you don't always catch things like these flares, for example. So I think there's also some work that needs to go into the search algorithms once LSST is around. Oh.
There's a lot of periodic things going on, gas accretion and so on, that sort of might overlap and cancel and so on. So if you find any periodic feature is this already a smoking gun for? I mean,
I think, yeah.
Exclude out of periodic?
I think, yeah, so periodic features are, well, they're usually due to orbits because gravity is good at being periodic. But does it have to be the orbit of a supermassive? It could be, for example, maybe a long-lived hotspot in a disk. Need a way to differentiate that from an orbit. Could be, well, if you have precession of some disk, but then that precession is usually caused by a companion as well. So I think periodicity usually has something to do with orbits, and I think that's relatively robust, but pointing that to the orbit of the right system of masses, I think is part of it. So yeah, if you can really show periodicity, I think that's telling you there's something orbiting there. But then you would expect, for example, lensing has to happen. So if you see a bunch of these periodic things and there's no lensing ever, then that means either these edge-on systems are very obscured or they're not black holes that are compact objects that are doing the lensing. So I think it's just important to push these models forward and ask what has to be there and use that to yeah. Yeah.
Surprised that the lensing is so high because you really need to be aligned perfectly, right? For the Doppler, it doesn't lock.
Yeah. But it's not that bad, actually. Those probabilities reflect those inclinations that you need. And because for these probabilities, I'm just asking that this ring, which is the orbit, say the smaller secondary around the primary lens, when it goes behind the primary, just overlaps with the Einstein radius. And if the separation is very close, for example, when you approach merger, that's almost every inclination. So because it's in a close binary system, I think your usual intuition about alignment is a little bit changed. So it still has to be relatively well aligned, 10 degrees or something like that, but it's not, 0.01 from. Yeah, it definitely is easier to get the Doppler alignment. Okay, with the next 15 minutes, I want to say a few things about, okay, step 2, the interaction of gas with the binary and what we expect the what I'll call circumbinary accretion to do to the orbit. Because this is, not the only piece, but a crucial piece in predicting populations. Okay, so I went through this step 1, step 2, step 3 before. Here's these steps on kind of a famous plot in this field from 1980 where this final parsec problem was pointed out. On the y-axis, you just have how long a binary spends at some r separation between the two black holes. So it doesn't have to be a binary at the largest separation. And the reason I'm showing this plot here is because you can see the initial final parsec problem argument is that when you go from the right far separation to the left, at some point, your time to merger becomes larger than the Hubble time. But these authors offered a solution to that problem in this paper, and they drew a dotted line here called T-gas, which says that can pop you over to the gravitational wave driven regime. And what was their argument here? That if you have gas falling onto the binary, then that binary is spinning around like a propeller. And let's just say in this argument that propeller then expels the gas at the inflow rate or some fraction of the inflow rate. And so it's giving its angular momentum to the gas, causing it to merge. And then if you want it to get rid of all of its angular momentum, it has to expel of order the same mass as itself. And if you plug in some numbers, that gas time scale is of order, 10 to the 8 years, which is less than the Hubble time. But would you really like to know what is the detailed kind of trading of angular momentum between that binary and the gas? And so to answer that question, that's why we look more deeply at this binary accretion problem. So binary accretion, people that work on planets here are familiar with this. Planetary migration is also based on this idea, circumbinary accretion, where here you have a binary with a really extreme mass ratio. So this is kind of Earth, Sun. Here's some planet orbiting in a gas disk. Here's the sun somewhere at the center of that excised region. And in planetary migration, we know, just, very cartoon schematic here, that planet creates a wake in the gas disk. That wake is sheared up by the Keplerian motion of the disk, and you create these spiral arms, which torque your binary. And in this case, shown through analytic arguments and also simulations since, you expect then that disk to push the binary together, to push the planet towards the star. And so it's interesting because this field has a long literature from the late 70s. And a lot of these migration prescriptions are still used to model supermassive black hole binary orbital evolution. But one big difference between the supermassives that we're thinking about in these systems is, an obvious one is just the mass ratio. The mass ratio here is 10 to the minus 6, but we're thinking more mass ratios near unity. So what changes? A lot, actually. And so a lot of my PhD work was actually thinking about when you go from the planet regime to the binary regime, what are the main differences? What is happening in the disk? There are these certain transitions where you go from steady to steady ring gap structures that you'll see here. These are hydrodynamical simulations, again, where dark red and black are low density and the white is high density. You get these gaps, and then as you go to more equal mass ratios, you get these really, time-dependent sloshing central cavities. And so as you imagine, this can affect what orbital evolution will look like, because your disk morphology has changed drastically. Okay, even so, in the 2000s, a number of simulations looked at this and asked, what does the orbital evolution look like? And I think the picture was that you still expect orbital in-spiral until probably about 5 years ago, when, starting with a few different studies, the picture started changing, and people were finding solutions where the binary wanted to expand, right? It seems a little counterintuitive. You put, again, a satellite into an atmosphere and it falls into the Earth. It doesn't go out further into space. So what I wanted to try and do, and I think Alessia Francini gave a talk here, and she probably talked about this a bit. So I wanted to see if I could just give you, maybe not a full explanation of why, but maybe show you how we compute this. And then we could talk about it more later. And then I wanted to see if there's time to show you some results for orbital evolution for eccentric binaries. But let me just go through this very, very quickly and see if we get a feeling for it. So how do you do this? I think what helps us understand that this is a correct solution, the possibility of expanding orbits, is that we can do it these two different ways, and they agree. So 2 ways. The first is that, really, we'll call it direct force summation. We take a binary, and on its own, its orbit is not going to change. There's a semi-major axis A, eccentricity E, total mass, and a mass ratio. But then in these experiments, we solve the 2D vertically integrated isothermal equations of hydrodynamics for the fluid surrounding the binary, these movies we've been seeing. And we simply ask, how does that fluid affect the orbit, by saying there are 2 conserved quantities, the specific energy of the orbit and the specific angular momentum of the orbit. And if you take time derivatives of those, you can just ask then, if those are changing, then the orbital elements, semi-major axis and eccentricity, are changing. And to ask how they're changing, we need to measure from the simulation what are these time rates of change. The torque, specific torque, and essentially the power change in energy of the binary due to the gas forces in the disk. So this is very straightforward. You have to just make sure that you're running at high enough resolution to get accurate forces. Okay, so what we usually find generally, we'll get back to this, is that this outer circumbinary disk, these kind of streams out here in this cavity region, really want to pull back on the torque down the binary and push it towards merger. But when you include gas from this inner region, it's doing the opposite. And depending on the parameters, the disk parameters, either can win. So in some cases, you can have an expanding orbit. Okay, that's really just, we calculated and that's what we find. But I think there's a little more possibly a little more intuition by looking at the second method, which you can only do for circular orbit binaries. And it goes something like this. So just like there is for a steady state disk, a constant accretion rate, there's for steady state solutions to azimuthally average disk, there's a constant accretion rate. There's also a constant global angular momentum current in disks. And you can see that, I'll just go through this quickly. If you write down the angular momentum conservation, where little l is again the specific angular momentum of say a ring of material in your disk, and big sigma is the surface density. And on the right, you have T, torques due to viscosity and torques due to the binary gravity. Okay, in steady state, that looks like this, where you have this constant m dot accretion rate in your disk. And if you integrate this in R, simply enough, you find that there is a constant quantity given by this combination of, so this is just an advected angular momentum. You have a ring of gas, angular momentum is moving through that. And these are the torques applied to that ring of gas. And this combination of torques, when you integrate here, there's a boundary condition, right? So if there's no boundary torque, then that's just equal to 0. There's no angular momentum flowing through the disk. But when you have the binary coupling to this disk at the inner edge, you possibly get a non-zero boundary term, and it's this global quantity, this angular momentum current. So it's not obvious how to predict what that should be a priori, but we can run simulations and measure this quantity. Oops, that's what I just told you. So, right, we can measure this quantity in simulations and ask, what is this global angular momentum current? And that has to be Newton's third law, give you what angular momentum is being dumped onto the binary. And so what is the evolution of the binary in this case? And that J dot B is what we measured from the direct force summation. And so this is from a simulation by Diego Muñez, where he showed from a time average simulation what are these components. So you can see this advected part blue, this viscous torque in green, and this gravitational torque in yellow. And when you compute this quantity, you get something time average that's, roughly constant. And what you get is a positive value, meaning that this coupling of the binary to the disk is causing mass and angular momentum to flow onto the binary. And when you compare that at high enough resolution to what we did with the direct force summation, you find that they agree. So this kind of argument is why I believe that I'm quite sure these results for expanding binaries are correct. And in the past, I think some of these things were missed, not always in a bad way, but for example, a lot of the early simulations excised the binary. So if you're doing the direct summation method, you miss the positive torques from the mini disks. And at the same time, I think you could have got the right answer if you asked what is the inflowing m dot L, specific angular momentum at this inner edge, and added that. Then I'm pretty sure we've done that now. You get the correct positive torque. Just a number of things like this. But what we're doing, and okay, so I'll in a moment say that something about how this changes with binary parameters. But I just wanted to advertise what we're doing now is trying to really nail this down with the community with a code comparison, because for a while it's been back and forth on, is this expanding binary the correct result? What part of parameter space is this result correct? And what we've been doing is there's a group of people now with about 10 different codes who are really nailing down this, simple, kind of simplest test problem where we expect the binary to expand and making sure we agree. And when we agree, and then using that to now push parameter space to, maybe outside of these kind of specialized cases where you get binary expansion. So this is something that we hope to finish soon, and I think will be pretty useful going forward. All right, and possibly interface with this new Lisa code comparison. Okay, but so I want to finish up here by saying that these expanding orbits happen for a specific set of disk parameters. So the disk can have a certain thickness, it can have a certain viscosity, and specifically for circular orbit binaries. But a lot of the work now is finding that, say you change disk thickness. Here's a plot of some work by Chris Teedy, who's a postdoc at NBI now. He shows that when the disk is relatively thick at this kind of aspect ratio of 1/10, you get these expanding orbits. So the total torque on the system is positive. But as you make the disk thinner and thinner, this drops to decaying orbits again. So it's a function of the disk parameters. Same thing for the mass ratio. This is a paper I wrote with Paul Duffel a few years ago, where we looked at expansion versus contraction as a function of mass ratio. For near equal mass systems, the system does want to expand, but below a certain transition mass ratio, that again changes sign. And another study I did with Paul is that we said, well, those are circular orbits, but what if we look at eccentricity, because these systems should be eccentric in nature. And so this kind of complicated plot, let me try and explain this as one of the last things here, because I think this is a pretty interesting result. So what did we do in this study? You notice we have these weird two continuous curves. So let me show you what I'm plotting here. We did a numerical experiment where we started with these simulations I've been showing you with a circular orbit binary. And then we very, very slowly, over tens of thousands of orbits, increased this eccentricity. Adiabatically was the idea. And at every point, we measured what is this semi-major axis growth rate and the eccentricity growth rate. So semi-major axis is in purple. Above zero, once it's expanding. Below zero, it's contracting. Orange is the eccentricity growth rate. Below zero, it's circularizing. Above zero, it's wants to get more eccentric. So at zero, you see that's the expanding circular orbit that we just looked at. That's just the very left point. And what's nice is that if you go to the right, the eccentricity rate is less than zero. So that's a attracting point. You're not always going to be moving away from there. And so what you find when you look at this kind of phase space here is that you have two attracting points in a divider, one at zero, circular out spiral, but also this very interesting one at an eccentricity of about 0.4. And what we found happens here, if you analyze this a little further, because you'll notice that A dot is also zero there, due to this really interesting transition, hydrodynamical transition in the disk, that what happens here is you have an in spiral, and that in spiral sticks to this eccentricity of about 0.4. And so, I mean, currently we're expanding this picture in a few different ways, which I could talk about with you later. But I wanted to end on one really interesting thing that's not published yet, and this will take 1 minute. And that is, we had this KITP conference on circumbinary accretion earlier this year, and it was to bring together people who are working on this problem, but for stars, planets, black holes across fields. And everything we'll be talking about today, black hole binaries, we don't really have observations, but the stellar people, maybe there's some in the room, they do have observations. And so the question is, can we learn anything, constrain anything about the theory we're trying to work out from these observations? And one really promising thing that came out of this conference that we're working on finishing now is that if you look, so again, we don't have black hole binaries, but Kepler, for example, has looked at tons of binaries, and it has a lot of eclipsing binaries, hundreds of them. And eclipsing binaries, you can measure the orbital parameters really well. And from that, you can plot the black histogram here. Kepler eclipsing binaries, what is the distribution as a function of their eccentricity? And you get this histogram. Now, if you take this blue dashed line, which is a prediction for some initial distribution of these systems when they're formed in a circumbinary disk, and you evolve them with this, predictions from our simulation, what's interesting, and again, this is preliminary, is that when I showed you before, there was these attracting solutions, but there was also a kind of repulsing solution. And what you see in the data is that there's a 5 sigma deficit in binaries in this eccentricity. So we're going forward trying to understand if we can learn something from this, but I think it's pretty exciting going forward that we might actually have a way to test some of these models, but we'll see. So that's it. Thank you very much.